That's fine.
Okay, great. Thank you.
All right, great. Well, let's see. So I can tell you a little bit about some of the things that I've been up to in the past couple of years and in the last 40 years. These are very connected because the things I've been up to in the last couple of years build on this tower that I've been kind of constructing for the last 40 years. It's a tower that's sort of a mixture of science and technology. And most recently, it's led us to a whole bunch of basic science that I've been really surprised about. It's actually quite amazing. I thought it was things that were 100 years away, and they're sort of happening now, and that's pretty exciting to me. The thing that's even more surprising is that I thought this was basic science, and if it had applications, it'd be like, thinking about in 1687, wondering, what will the applications of calculus be? Will they allow us to fly artificial satellites and so on? And that was going to be, it was going to be 300 years away. But it turns out that this basic science also seems to have a bunch of near-term, sort of both modeling and technological implications. And maybe I'll get a chance to talk about a few of those as well. But let's start off with talking about some science, and maybe I should tell you. Well, let's see. I can jump into sort of the big picture here. The main thing that's sort of the big surprise is that it looks like we have a pretty good idea of what sort of the machine code of physics, the universe actually is, which is awfully surprising. And, it's gone up and down over the centuries whether people thought, yeah, we're close, we're going to get it, we're going to figure out sort of how physics works, versus it's far away, it's, it'll never be figured out. It's a bottomless pit. There's going to be no answer to how the universe actually works. The surprising thing is that not only does it seem like we have a pretty clear idea of what the quotes machine code looks like, it also turns out that most of the approaches to mathematical physics that people have been pursuing the last, I don't know, few decades have places. And I thought we might figure something out. It might be incompatible with the, I don't know, spin network, string theory, causal set theory, all these kinds of things. But actually, no, it's not. It's essentially a machine code, and these things fit into it. And people are now figuring out, there's quite a large group of people working on this by now, figuring out, among other things, the connections to all these different, all these different kinds of areas. So it's a very encouraging thing. All right, well, maybe I should start off by talking a little bit about what we figured out so far. At this point, it's becoming a fairly deep stack that we figured out. So I'm not going to be able to do justice to everything here, but I'll try and give you the basic ideas. Let's see. So let's start off. Well, there's a website you can find. Actually, we've been doing this project as a very open science project. So we live stream most of our internal meetings about the project. We put up all of the internal working material. You can find all of it here. You can find this. I think we did last year 380 hours of live streams, I think, roughly. Not all specifically about physics project, but about related things. So it's sort of an interesting experiment, not only in the content of the science, but also in the doing of the science. Okay, let's talk about sort of the machine code of physics. So this is kind of a visual guide to what's going on, and let me try and talk through this and explain some of what's happening. So the first question is sort of what is the universe ultimately made of, so to speak? And the most obvious feature of the universe is space. And usually one doesn't think of space being made of anything. I mean, since Euclid on, it's just space is a place where you put things. You say there's this position, et cetera, et cetera, et cetera. It's not made of anything. Well, you probably would have said the same thing about something like water a couple of hundred years ago. It's not really made of anything. It just flows. It has all these properties and so on. And you can, but in fact, it turns out it's made of something. It's made of discrete molecules bouncing around, and only in aggregate does it have these fluid properties and so on. And so one of the starting points for our approach to physics is the idea that space is actually made of something. It's made of what one can think of as atoms of space. These are completely abstract objects. They're things where the only thing one knows about them is that they are different from other things. So each one could be thought of as having some kind of unique ID, but it's just an abstract element. And the only thing you know about these abstract elements is how they're related to each other. So in a sense, there's no coordinate system, there's no positions, all you have is a big bag of abstract elements. Maybe in our universe today, perhaps 10 to the 400 of these abstract elements. And these abstract elements, these kind of atoms of space, the thing that we define about them is how they're related to each other. And so we can sort of describe those relations in terms of a hypergraph. We say that every atom of space, so for example, we might say, I don't know, these are atoms of space 1 through 4, and they're related, atoms 1 and 2 are related like that, and so on. We could represent that by a graph. And now, so the idea is that everything we see in the universe is ultimately just a giant hypergraph. So that the structure, that space at its smallest scale is just made of these atoms of space connected in this kind of hypergraph structure. So then the question is, okay, so for example, with that setup, the basic idea is that's sort of the data structure of the universe, and its process of evolution is it has some rule that says whenever you see a piece of hypergraph like this, rewrite it to be a piece of hypergraph that looks like that. So for example, we might start off with, we might have, let's say this is the rule, which just says whenever you see a piece of hypergraph that looks like this, rewrite it like that. We start off with some initial condition for the thing that looks like this. We keep rewriting it, we keep rewriting it, we keep going. And after a while, we'll get something that looks like this, and we keep going even further. What is this thing limiting to? Well, it turns out it's limiting to a thing that is like a continuous space. It happens to be a 2.6 something dimensional space, but it limits to something that is like ordinary space. Now, here's an example where we can kind of more easily see what it's limiting to. This is just the first few steps of a particular rule. Let's see, the limit of that rule is just this two-dimensional grid. And we could look at a whole bunch of other rules here. We could say something like this. We could look at the limit of that, look at some other limit. There's another limit, which is roughly a two-dimensional grid on a curved surface and so on. So the concept here is that at the lowest level, at a length scale, we don't know the length scale. There's one parameter in this theory, which is basically an elementary time, elementary length. You can move it around to different places, but in a very kind of rickety estimate for the elementary length, it might be around 10 to the minus 90 meters. So very small compared to the Planck length, for example. And so at that length scale, in effect, this is the structure of space. So the question is, then we start off thinking about, so we imagine that the only thing that exists in the universe is space. And so everything that we know about the electrons and quarks and photons and all that kind of thing, all of those things are essentially persistent topological structures in this network that are persistent with respect to the evolution of according to these particular rules. So, for example, kind of the way one thinks about that in I don't know, I assume you guys know about these kinds of things. And the thing I've long studied, cellular automata, where you just have a line of cells, each black or white. This has a very simple rule that just has two possible colors for each cell. In this case, just with that simple homogeneous rule, you have these definite structures that are, in a sense, persistent particle-like structures that develop. And so the idea here for physics is that that's how particles work in the physical universe, in this hypergraph that represents the structure of space. It's more complicated there. It requires mathematics, which a quote from a well-known graph theorist who I asked about this a few years ago said, I need to know various theorems about graph theory, said, well, those are all good questions. Come back in 100 years and we may know the answers to a few of those. So it's kind of, we're on our own as far as figuring that out. Now, so kind of the idea here, as I say, is we're thinking about everything in the universe is just associated with the structure of space. And and then the thing we're then defining is, well, okay, if that's the sort of lowest level structure, what about well, what can we say about the structure of space as defined in this way? Well, it doesn't intrinsically have anything. It doesn't even have dimension. So, for example, we'd have some structure like this, and we say, what's the effective dimension of that thing? Well, what I'm doing when I'm showing these graphs, I'm just showing a particular human visually convenient layout of the graph. So any particular graph could be laid out in many different ways, but we can make measurements on these graphs. So for example, we can say, what's the effective dimension of this limiting thing that corresponds to the structure of space? And so we can work that out by just working out, we start off from some node in the graph and we go a graph distance r away from that node. We progressively build up this kind of geodesic ball around this point in the graph. And then we ask, for example, how many nodes are there within that ball when the ball has radius r? And if there are r to the d nodes in that ball, then we can think that this effective dimension of this limiting structure is around d. And similarly, we can go on and we can measure that and we can find out, yes, something has dimension 2.6 or something. We can also go and say, well, what are the corrections to that? So in flat space, the volume of a ball, the volume of if we work out the area of a circle, it's pi r squared, but if we have the circle on the surface of a sphere, there's a correction term that's proportional to the curvature of the sphere. So we can work out the same thing for these structures that are made by rewriting these hypergraphs, and we find out that yes, when the thing looks curved, there is indeed a correction to that growth rate of the geodesic ball. That correction, the first order correction, is proportional to the Ricci scalar curvature, which is interestingly the thing that also appears in the Einstein equations. So, okay, so we've got this kind of idea that the structure of space is associated with this giant hypergraph that is growing. What's time? Well, time is this kind of inexorable process of evolution of the rewriting of this hypergraph. And one of the things that's kind of a key idea here is something that comes out of part of the sort of stack of things involved in building up to this. It's the following thing, that when we have even a deterministic rule operating on some structure, that even if that rule is simple, the behavior that it can produce can be very complicated, and in particular complicated in a computational kind of way. So my sort of favorite example of this from studying cellular automata. So here's a typical cellular automaton. It's got a line of cells, each one is black or white. It's got a rule that just says for every triple of cells with this configuration, this determines the color of the cell on the next step. So you might say, well, there's a very simple rule. It's obviously going to do very simple things. That's what I thought back in the early 1980s. Here's an example of a rule where if you run it for a little while, it will make a nice fractal pattern. If you then sort of do the computer experiment, you say, let's just go out into this computational universe of possible programs and see what's out there. This is what you get from the first few programs. And this is my favorite, all-time favorite science discovery. This is rule 30. This is its rule here. We just started off from one black cell at the beginning, and it grows this seemingly quite complicated pattern. You keep going on for a while. There's some regularity that you can see in this pattern, but many aspects of this pattern look, for all practical purposes, completely random. Like if you look at the center column of cells here, there's no statistical regularity one's ever been able to find in that sequence of cells. Well, so there's a question of sort of how to think about what's going on in a system like this. And it's all related to this thing I call the principle of computational equivalence. And kind of the idea is that you can sort of think of the process that's going on here as a computation. You start from some initial condition, you're then running according to this rule and generating some output. But there's sort of a question of how sophisticated is that computation? And if we look across all kinds of different systems, whether it's cellular automata, whether we look at Turing machines or other kinds of things, we can even look at partial differential equations if we want to, but lots of different kinds of systems, it will turn out to be the case that when the behavior is not, in a sense, obviously simple, we will find that the behavior, that what the sort of the assertion is that when the behavior is not obviously simple, it will be computationally as sophisticated as anything. So that means that in principle, that has many implications. So for example, one thing it means is that one thing it means is that this system, so we can think of predicting what's going to happen in the system. So this system is doing a computation, we're doing computation to predict it. If this system is not that sophisticated computationally, we can easily jump ahead and make a prediction and say in a trillion steps it's going to do this. But in fact, this principle of computational equivalence says that above some low threshold, essentially every system is equivalent in its computational capabilities that it shows. So that means in particular that our brains are no more sophisticated than this system. And so that implies that when we look at this system and we try and sort of outrun it computationally, we won't be able to do that. And that leads to a phenomenon I call computational irreducibility, which basically says that when you are trying to figure out what's going to happen, you can figure it out by doing every step of the computation, but there's no way to reduce that. It is a computationally irreducible process. And there's also other implications of this principle of computational equivalence. It has a bunch of predictions, like that these systems will be capable of universal computation. And we know, for example, for the Rule 110 cellular automaton, we know that, which is the one I was showing with all those particles, that that's capable of universal computation. We know that the very simplest Turing machine that I found years ago that could conceivably be universal is in fact universal. And so that's another sort of piece of evidence for this principle of computational equivalence, and kind of goes on. But the main point is that there is this kind of there is this process whereby even a very simple rule can produce behavior that is computationally undecodable. And that, by the way, is related to many things. For example, one thing that it's related to is the second law of thermodynamics. This is an example of reversible cellular automaton. And the basic point here is that to a computationally bounded observer, to something sort of an observer like us, there's no way to figure out that this thing, when you have it down here, comes from this kind of simple special initial condition. So in a sense, the second law of thermodynamics is a reflection of computational irreducibility for processes, in that case of classical molecular dynamics, that leads to something which we can't decode. We can't say it's anything other than random when we look at it, because we don't have because it is, in a sense, doing irreducibly more computation than we're doing. So, okay, so that means that in terms of our models of physics, we're saying here, we've got this hypergraph, it's being rewritten according to this rule. It might be a simple rule, but that process of rewriting is producing sort of an irreducibly complex, computationally irreducible thing. So the reason that that's important is that, in a sense, the reason that space appears continuous as it does to us is because of the way that we are as observers, and the fact that we have, for example, computationally bounded capabilities for observing the system. Or at some very simple level, we're big compared to the atoms of space, but we also don't decode all the detailed motions of the atoms of space, so to speak, or the detailed processes that are going on there. So what happens here is we've got this system and it's being progressively rewritten. We've got this idea that space is this extension of this hypergraph. Time is something not very much like space. It's the progressive computational rewriting of this underlying structure. So that's something which, in terms of the last 100 years or so of physics, is something that might seem surprising, because originally, I don't think Einstein was very big on space and time being the same thing. I think Minkowski was very proud of the fact that the number theory he'd studied had quadratic forms that looked like x squared minus t squared. And it's like, that's the thing. Space and time are the same kind of thing. We'll just put them together in a 4-vector and all will be good, so to speak. I think the concept that space and time are the same kind of thing, which seems intuitively not that convincing anyway, is something which is rather misleading. So the question is, in this setup, when space and time aren't the same kind of thing, how do things like relativity arise? Well, it turns out, if you think about being an entity that's embedded inside this hypergraph that's updating itself and so on, you have a certain view of what's going on. In particular, the only thing you really are sensitive to is the causal graph. That is, what you looked at from inside the system. The only thing you can tell is what the sequence of updatings that happen to you are and how they relate to updatings that happen to other things. So sort of a thought experiment. Imagine that the whole universe was run by a Turing machine. It's got just this one head. The head is running around all over the universe and so on. And we could think about it as we say, but that couldn't possibly be the right theory because after all, you and I are getting updated at the same time. But how would we know that? Because I don't know that I've been updated until I don't know you've been updated until I've been updated. And so if you work that through, and I did this actually back in the 1990s, what ultimately matters is just the causal graph of relations between updating events. And so in that particular case, there is a causal graph in which there is updating of you and updating of me, and we can consider those things to happen simultaneously. In this case, we'll be building this kind of causal graph that represents every time we update a piece of this network, we represent that as an event. And we can say, well, what's the graph of relationships between those events? And here's an example of such a graph for that same rule I was just showing you. And so the yellow things are the events. And this is saying which event uses input from a previous event. So let's look at a simpler example of that. Let's see if I can pull one up. Let's say we are just looking at, let's do this. Let's say we're looking at a simpler analog system where we just have a string of A's and B's, and we have a rule that says whenever you see BA, it gets replaced by AB. So each one of those updates we can think of as an event, and here we've got a collection of updating events that in this case has the result of sorting this string. So this is, and so the way these events work is the causal graph is the thing that says this event down here takes its input from this event up here. So these are causally related. And so we can draw on top of this, we can draw a causal graph that represents the causal relationships between these updating events. Okay, so important fact, actually it's true for this particular rule here, there are many different choices for what gets updated when. Which BA do we flip to AB at which moment? Do we flip this one? Do we flip that one? Which one do we flip at every moment? Do we get around to flipping one up here, or do we not flip that one yet, and so on? And so, like that one there, do we flip that one yet? No, we don't. We wait until here to flip that. Okay, so an important fact about a system like this is it has what in mathematical logic is called Church-Rosser property, confluence. It's gone by many names. It's basically the property that it doesn't matter in which order you do the updates. You'll always, in this particular case, you'll always get the same answer. In more generality, there's a property we call causal invariance that means that whatever micro updating order you use, you will have the same causal graph. And so what that means is when we think about one of these systems, what we're saying is that to an observer embedded within the system who only knows about the causal graph, it doesn't matter what the microscopic sequence of updatings is, they will always conclude that the causal graph is the same. And that's what leads to special relativity. What basically is happening is that you are making a kind of a foliation, the reference frame that you are using to observe the universe is a slicing of this causal graph, and each slice is what you say are the events that you consider to happen simultaneously in time. And so you can reconstruct your view of space by saying, this is the sequence of, this is the collection of events that happen at the same time, and we can look at their relationships by looking at essentially little light cones here to see how these events are related, and that's sort of a reconstruction of the structure of space. But then if we had a different reference frame, if we were traveling at a different speed or something, we would have a tipped reference frame here. And in fact, if you work it out for a very simple case, here's a very simple causal graph, and we can look at kind of the tipped reference frame on this very simple causal graph. And if we sort of rearrange things to the observer thinks that time is just progressing straightforwardly, this is what we would conclude the causal graph, how the causal graph might be arranged. And it's a simple matter of trigonometry to see that this gives you Lorentz transformations. And in fact, you can even see that at the level of these string rewriting systems. This is kind of the rest frame of the string rewriting system, where sort of all the computational effort of string rewriting was spent in actually doing the rewriting of the strings. If you go to a boosted reference frame where you're sort of traveling through the string as well as updating the string, you will find that sort of computational effort of traveling through the string is using up some of your sort of computational resources. And so you end up updating the string more slowly. And that turns out to be exactly time dilation. And rather amusingly, all the formulae work out exactly the same as they do in standard special relativity and Lorentz transformations and so on. So causal invariance, this property that certain rewriting rules have the feature that the causal graph you get, even though the microscopic updating order is different, that all of those, anything with causal invariance inevitably shows relativity. In fact, it does more than that. It gives one general relativity. And we can start seeing that in more detail here. We can actually look at, I mentioned you can get, by looking at the kind of these geodesic balls in this hypergraph, you can build up, you can get the first order correction is the Ricci scalar. You can do that in the causal graph, and then you get space-time Ricci scalars and Ricci tensors and so on. And when you build that whole thing up, the question is, what is the effective continuum limit of the behavior of this system? And it's kind of, the derivation is very similar to the derivation of the continuum limit for a fluid like water from molecular dynamics, where you can derive with certain assumptions, which people have been trying to nail down for the last 150 years, and there are definitely mathematical loose ends there, but essentially one can derive the Navier-Stokes equations from fluid flow from molecular dynamics. And so the question then here is, what are the equations, what are the continuum equations that one derives from this rewriting process with all its computational irreducibility and its randomness that leads one to be able to take statistical averages and so on? Well, it turns out what one derives is Einstein's equations. So the equations for the large scale structure of these hypergraphs are Einstein's equations. Now, footnote to that, it's a bit more complicated because this can be in any number of dimensions. And so, and the dimensionality can actually be a dynamical parameter. So for example, what we find is that what we expect is that in the very early universe, probably the universe was effectively infinite dimensional, and it gradually cooled down, reaching its current three-dimensional state, and we can't derive the number 3 yet. It probably means that there are dimension fluctuations that might have been left over at the time of cosmic microwave background and things like that. And there's a lot of interesting physics about, what does a photon do when it propagates through a region of 3.01 dimensional space? And there's a whole bunch of essentially classical electrodynamics to figure out about how would we detect dimension fluctuations, for example, in the universe from looking at properties of photons and so on. So, but the main point is the continuum equations we get are Einstein's equations. Now we can start looking at things like the propagation of geodesics in these graphs. That would be, if we're in sort of flat space, the shortest distance between 2 points is a straight line. If the space is curved, it's not. That's how we, and the way we account for gravity in standard general relativity is we say space is curved by the presence of energy momentum in space. So the next question for this is, well, what is energy momentum? I must say that I thought that would be a very complicated question to answer. It turns out it's rather straightforward. It turns out that energy is basically a measure of the amount of activity happening in the network. So it's a little bit tricky to measure energy density because you have to know what volume is, and volume is something which is an emergent property of these networks. But slightly more precisely, if you make space-like hypersurfaces, if you just slice the causal graph in a series of slices that correspond to successive times, they're the space-like hypersurfaces. If you make a series of space-like hypersurfaces and you simply ask in the causal graph, what is the flux of causal edges? What is the flux of connections between events that slice through, that poke through the space-like hypersurfaces? The flux of causal edges through space-like hypersurfaces is energy density in our models. And similarly, the flux through time-like hypersurfaces is momentum density. And mass is associated with essentially the it's the parts of the activity that doesn't change from one space-like hypersurface to the next. So, okay, so that's kind of the interpretation of energy as activity in the network. And it turns out then what happens is that the presence of that activity in the network causes geodesics to be deflected. So when there is activity in the network, you're effectively changing the density of edges and so on. And the end result, when you work out the mathematics of it, is that you deflect geodesics. And you deflect geodesics according to exactly the geodesic deviation equations and all the things you expect in general relativity. So in the end, what you're finding is that you have a, you've got this idea that energy density in this represented by activity in this hypergraph causes deflection of GD6, which is what you would expect in curved space, and the mathematics all works out. So you can work out, there are things like black holes, for example. An event horizon is a very straightforward thing. It's simply a way in which there's there's a causal disconnection in the causal graph. So for example, here's a very simple event horizon. There are events over here that have causal effects on subsequent ones, but the events over here do not have causal effects on the events over here. This is a cosmological event horizon between these two different parts of the universe. And you can have one-way event horizons that are like black hole event horizons and so on. And for example, when you look at black holes, like a standard Schwarzschild black hole that has a space-like singularity, what does that mean in terms of this model? It means in classical general relativity, it means that all GD6 are finite length. What it means in this model is that there comes a moment where no more rewrites can be done, where the causal graph just ends, where there is a final event and then it's all over. The hypergraph is fixed. So in a sense, time ends there. And so that's what's happening in at least a Schwarzschild black hole, is you have this place where essentially time ends. That is equivalent to all of these systems we can think of in much more abstract forms in terms of mathematical logic and so on. That is a so-called normal form being generated in a term rewriting system in mathematical logic, which is kind of an equivalent kind of setup. So, okay. So that's a little bit on the sort of story of general relativity here. One might ask, do we know we got the right answer? Well, here's a good piece of evidence, other than the mathematical derivation of Einstein's equations from this underlying dynamics. A good indication is that people are actually using this to make practical numerical relativity systems. So the same thing as back in the mid-1980s, I did this actually for fluid dynamics, of realizing that there was a simple cellular automaton that would, in a large scale limit, reproduce the Navier-Stokes equations, various footnotes to that, but basically that was the idea. And one way of doing fluid dynamics is you start off from the Navier-Stokes equations, which are continuum equations, and then you say, on a computer, I'm going to make finite elements, I'm going to discretize them. We've now got pretty good stuff in Wolfram language for doing that, which I encourage people to use because it's really nicely integrated with computational geometry and lots of other things. But in any case, that's sort of the traditional approach, is you start from the continuum equations, you discretize them to solve them on a computer. What's happening here is that you start from something discrete. You start, just like with the molecular dynamics, you might start from the Navier-Stokes equations, or a cellular automaton in that case. You say, let's put in a lot of molecules, a lot of cells in the cellular automaton, and let's then look at the effective aggregate behavior of that and see what happens. Well, you can do the exact same thing here for the Einstein equations. And indeed, a young collaborator of mine working on this, Jonathan Gorard, has a nice paper where he actually has black hole mergers computed. I'm sort of surprised they work as well as he claims they work, because he doesn't have a lot of there's the number of atoms of space across his black holes is not very big, and it's not obvious that you would get the right limiting, how far you have to go to take that limit. But the basic point is that one can use these methods as actually a scheme for doing numerical relativity when one is just starting from sort of the atoms of space and working upwards. It's kind of fun because, in doing that with numerical analysis, one often has to worry about, oh, let's make an adaptive scheme and let's put more points in when more points need to happen. In our models, the adaptivity is because of the structure of space. Adaptivity is associated with energy momentum because that's where there's more activity in the network, and the curvature is associated with the same thing. And so in a sense, the thing is automatically adapting by its very nature. So it's very possible that this will end up getting used as a practical system for doing numerical relativity, because it's actually pretty efficient and so on, before we can find any kind of experimental verification that, yes, if you really look at sort of a good enough gravitational microscope, you will start actually seeing down to the atoms of space. One of the things that's interesting in fluid dynamics, for example, you could say, how do you know from fluid dynamics that fluids are made of molecules? Well, you can look at Brownian motion, you can look at hypersonic flow, things like this. The question is, what are the analogous things for space-time? And it looks like there are some effects in rapidly spinning black holes where essentially the black hole is hanging by a very few causal threads, and one expects, for example, shot noise and the gravitational waves that are produced and things like this. How hard that is to detect, we don't know yet. It's one of the big things that's happening. I would say many things with this project are happening vastly more quickly than I would have expected. One thing that's definitely still sort of getting started is working out the experimental implications, because a lot of that involves a big depth of traditional physics beyond sort of knowing about what's happening kind of at the machine code level. Okay, well, so that was a little bit on general relativity and gravitation. Just for fun, I might comment on, I think you guys are talking about propulsion systems and so on, and maybe just for fun, I'll comment on faster than light travel, which is something one could sort of ask about in a system like this. See, one of the things that's true about, one of the things that's in this system, the structure of space-time is much more flexible than it is in general relativity. In general relativity, when you have a black hole, for example, you have to punch a hole out of the manifold that represents space-time to even have the concept of a black hole. And you can't have sort of continuous topology change. In our setup, you can have topology change because there is no topology. Topology is an emergent thing. So, for example, one of the bizarre phenomena you can get are things I call space tunnels, which are sort of things which connect different parts of what is mostly sort of space as it normally is. There is a space tunnel, which is essentially a different dimensional thing that connects different regions of what you would normally think of as space. But there's another effect, and the other effect works like this. So the issue is, imagine that you're in a gas and it's got molecules bouncing around, and you ask, how quickly can you get across the room using molecules? Well, most of the time, the molecules, they're all colliding, and there's diffusion, and it's a pretty slow process. But if you were able to be smart enough, if you were kind of a Maxwell's demon operating down at the level of molecules, and you could hop on one molecule, you could say, oh, I'm going to collide with this one, I'm going to collide with that one, I'm going to make this sequence of choices for what molecules to be on. You could actually get across the room at the speed of sound, probably, by making the right choice of which molecule to hop on next. Then you wouldn't be dealing with diffusion. Diffusion is a phenomenon that is a consequence of sort of the computationally bounded observer who isn't going and hopping on the right molecule at every moment. Well, so how do you do that for space-time? Well, at the level of the atoms of space, there are all kinds of things that are going on. And one of the things that happens is, if you look at the concept of a light cone in, there we go. So here's a causal graph, and this shows a light cone. So this is, you look at that event and you say, what can be affected by that event? It's all these events here. Okay, so the question is, where are those events in space? When we assign a meaning to how space is extended, this light cone is what it is. But the question is, how do these events map onto what we normally think of as space? And so what you realize is the thing that we normally think of as space is created as this kind of emergent thing. And so if we can get a path through here, which is potentially a path that goes, let's see if I have an example here. Let's see. Is this an example? Maybe a little bit. Okay, so this is showing that light cone superimposed on a reconstruction of space. And so the issue is this light cone, does it have tendrils that stretch out? The main part of the light cone will reflect the actual structure of space in 3 dimensions and all that kind of thing. But there will be, in general, there will be little tendrils, inevitably, because of the sort of computational irreducibility, kind of molecular dynamics like thing that's going on. There'll be little tendrils that stretch out further. Now, can you make use of those tendrils? Can you put anything through those tendrils? Well, no, not really, because the things you might put through are made of the same stuff that everything else is made of. In a sense, the question of what you can communicate along a tendril, that's kind of a thing. It reminds me a lot of the claim nobody will ever send data. I could see older people here, so some people might be amused by this. The old claim, you'll never be able to send data at more than 300 bits per second along a copper wire. which kind of denies the possibility of all kinds of signal processing and so on, and all kinds of things you can do with the data and the signal. So as it is right now, I don't think you can send anything through the tendrils that kind of extend beyond the traditional speed of light cone in space-time. But who knows what the future will bring there. But in this model, it's sort of inevitable that there will be these little tendrils that reach out further, although they will be tendrils that are small compared to the main light cone, which is determining how fast electrons can go and photons can go and so on. I just thought I'd mention that as a kind of amusing sideshow here. All right, so another big piece of this whole story is about quantum mechanics. And let's talk a little bit about that. So one feature of our models is you can't get away from quantum mechanics in them. You might have thought, well, we got this nice setup and it's describing space-time and so on, but quantum mechanics would have to be sort of wheeled in from somewhere else. Not so. Very sort of, in a sense, frustratingly from the structure of the model, you can't avoid quantum mechanics. The reason is this. The reason is that let's first describe the sort of basic difference between classical mechanics and quantum mechanics. In classical mechanics, a core idea is that definite things happen. So, you throw a ball, it goes in a definite trajectory. In quantum mechanics, kind of the big idea is definite things don't happen. There are many possible things that can happen, and all we get to observe is some aggregated probability that comes from the amplitudes of different things having happened. That's kind of the path integral type interpretation or kind of formulation of quantum mechanics. Okay, so in our setup here, what happens is we've got all these little updates that could be done, and we say, well, which update should we actually do? Well, all we're told is do an update somewhere. And the point is there are many different possible updates that could be done. In particular, there are many possible paths of history that can be generated by different sequences of updates. So for example, if we look at, let's look at an analogous setup here. Let's look at something that is just based on, let's say, rewriting strings. So this is, let's see, this is the rule, A goes to BBB, BB goes to A. We rewrite strings according to that rule, and there are many paths of history here. We can have this sequence of rewrites going down here. We can have a different sequence of rewrites going down here. Each of these is a different path of history. And the idea is that in our model of space and so on, based on these hypergraphs, there are also many different possible paths of history that can occur. And what we then are asking is, well, okay, with all those different paths of history, how do we tell what's happening? Well, one thing we can do, one question is, okay, so we could represent, let's say with the hypergraph, these are different possible hypergraphs that are being generated, and we see that there's branching and there's also merging of these different paths of these different possible histories. Okay, so one way we can kind of characterize what's going on, we can ask, yeah, I should have shown you, that's sort of the sequence of updatings that happen in a particular hypergraph. That's one possible sequence of updatings, but there are many different ones, and each path in here corresponds to a different sequence of microscopic updatings. And so one of the issues that, so to characterize that, we can say, well, let's say, okay, so a big question is, how do we observe what's happening? So we've got all these different paths of history, and you might say, well, that's hopeless because we know the universe has only one kind of definite history that occurs for it. But that's our impression. But remember that we are embedded in the system. So our brains are branching just the same as the universe is branching. So in a sense, the question of what you will observe in this kind of branching multi-way system, as we call it, is, how does a branching brain perceive a branching universe? And the key sort of idea is, as soon as the branching brain believes that there's a definite history, the branching brain will kind of conflate these different paths of history. And the question then is, well, is it consistent to do that? Or will something totally inconsistent happen if you make that conflation? Well, causal invariance guarantees that no bizarre, that it will ultimately, things will be consistent. We can characterize kind of what we're seeing at every moment here by what we call a branchial graph. Branchial graph basically is just telling one for two of these things, how are they related by common ancestry? How are they entangled with respect to the history of all these different possible histories? So we can draw these branchial graphs. These branchial graphs are in our theory, the map of kind of quantum entanglements. These things here are quantum states, And this is a map of sort of the entanglement structure of these quantum states. And one of the important things is that we can think about there being a kind of branchial space, these things laid out in this space that isn't physical space, it's this branchial space that's a different kind of thing. It's a space of quantum states. And so then we can ask questions like, well, what is the meaning of the coordinates in branchial space? It turns out the meaning of the coordinates is roughly, and there's much mathematics to do to nail this all down, but roughly the distance in branchial space is a difference in quantum phase. We can think of the phase of these states, quantum amplitude associated with these states, as having, usually that's characterized by a single complex number. In our models, just like we have to break apart space and time, we also break apart quantum phase and the magnitude of quantum amplitudes. The magnitude of the quantum amplitude is just associated with the number of different paths that allow you to reach a particular state. The phase is associated with the position of the state in branchial space. So what is this branchial space? It's this abstract space in which quantum states are laid out. And so, for example, one question we might ask is, if we start an experiment and we have some bundle of quantum states at the beginning, some superposition of quantum states, that's some region in the branchial space, and we let that bundle of states propagate forwards in time, what will happen to it? How will it move around in branchial space? Well, it turns out that the exact same thing happens as happens in our hypergraph. In fact, there's a thing, the multi-way causal graph, which is a generalization to both space-time and branch time. It's a kind of space plus branchial space generalization of the causal graph. That multi-way causal graph is something where we can ask questions about what is the density of causal edges in that causal graph and so on. Anyway, the end result is that just like the geodesics in physical space are deflected by the presence of activity in the network or energy momentum, so similarly, geodesics in branchial space are deflected by the presence of activity in this whole multi-way causal graph. And that activity we can identify with energy density, or in a more relativistically invariant way with Lagrangian density. And so what we're then finding is that the geodesics in branchial space are being deflected. There's motion in branchial space that is which is being affected by the presence of energy momentum in the system. So what does that remind one of? Well, in quantum mechanics, the Feynman path integral is e to the I times the action, which is the integral of Lagrangian density divided by h bar, and that's times time, and that is the deflection of a geodesic in quantum phase. And so in our models, that deflection of a geodesic, it happens in branchial space as it happens in physical space, both as a result of energy momentum. And so that means that what that's saying is general relativity, which leads to gravity, leads to deflection of geodesics and so on, that theory in physical space, it's the exact same theory operating in branchial space that is quantum mechanics, which I think is really a pretty, that's one of the most elegant things there are actually several more now, very elegant things that's come out of our model of physics, is that gravitation, general relativity is the same theory as quantum mechanics, but played out in a different kind of space. Now, there's also an interface between these. In this multi-way causal graph, there are projections onto space, projections onto branchial space. This is presumably, and a bunch of people are working on more details of this, but it is presumably if you follow sort of the string theory and things like that, the holographic principle, ADF-CFT correspondence, that is presumably the projection of the multi-way causal graph either onto physical space or onto branchial space, physical space being the ADS side, branchial space the CFT side. That bunch of details of that are getting filled in. But that's the, so now what can you do with this kind of view of quantum mechanics? Well, there are many things, but one thing that's been interesting is this maps into a thing called categorical quantum mechanics. You can, and it's actually now possible, we have, using this formalism, we can actually take a quantum circuit and we can compile it into multi-way graphs. We can then run theorem-proving systems as an optimizer for the quantum circuit. And I think we have the fastest kind of quantum circuit optimizer built not by doing quantum mechanics in a sense, but by compiling the quantum mechanics into our model of physics and then doing things which then map precisely back into ordinary quantum mechanics. Quantum mechanics is sort of a story of pure branchial space. Quantum field theory is a mixed story of branchial space and physical space, and that's a big, tangled, complicated mess mathematically, but it's looking pretty likely that we are going to be able to have direct ways to compute things in quantum field theory, and traditionally once had Feynman diagrams and once had lattice gauge theory, which works in Euclidean space-time. It looks like we will be able to have a direct way, just like we can make direct computations for things like for things in general relativity. We'll be able to do the same kind of thing for quantum field theory. So that's okay. So that's a little bit on that. I would say that there are a bunch of other things. So another thing is there's a maximum entanglement speed, just like there's a speed of light in physical space, there's a maximum speed of propagation of information in branchial space, a maximum entanglement speed. We'd really like to know what that maximum entanglement speed is, because that is the one parameter. You can move around what that parameter is. It's either, once we know the maximum entanglement speed, we know the elementary time, we know the elementary length, we know the elementary energy, all these kinds of things. The rough estimate we have is that maybe the maximum entanglement speed is around 10 to the 5 solar masses per second. If that's correct, one will be able to see its effects in large black hole mergers, because they'll be limited not only by speed of light, but by maximum entanglement speed. The thing that is something I'm chasing right now is whether in quantum many-body systems it may be possible to actually measure decently large maximum entanglement speeds. That's unclear as yet, but that's another kind of phenomenon. So let's see. Well, one of the things that comes out of all of this is that in this model where you have these multi-way graphs and so on, the observer is not merely an optional feature. The observer is necessary to tell what's going on. Otherwise, you have these many branches of history and you can't tell what's going on. One of the things that, so I want to, I think I shouldn't go on too much longer here, but what I've told you about is a little bit of sort of the pure physics side of our physics project. There is a whole set of other things that have come out in the last year or so that have to do with applying this formalism to many other fields. And let me mention one thing. Okay, so one question is, okay, so you've got this whole setup. What is the underlying rule? What is the rule that sort of runs the universe, so to speak? Well, that's in the lesson from thermodynamics might be, it doesn't really matter what the underlying rule is. We have molecules, the water molecules bouncing around, we have air molecules bouncing around. They both obey the Navier-Stokes equations of fluid mechanics. And we could ask, if we really cared, we could ask what the detailed molecular dynamics is, but for many purposes at sort of our human level, we actually don't care. Well, in the case of physics, the same thing is true. Computational irreducibility provides a sort of layer between what's actually going on underneath and what you actually observe. And in these continuum limits, it won't matter what the underlying dynamics is. But you could still say, it's still sort of this question, okay, you've got a particular rule that successfully can reproduce the universe. Why that rule and not another one? So I was very puzzled by this for a long time until I realized that the way to think about this is we have this multi-way system which says, take a rule and apply it all the places you can. But there's more that you can do. You can say, take any rule and apply it any place you can. And so you end up with a rulial multi-way system, a multi-way system where not only are you applying a particular rule everywhere, but you're applying all possible rules. Now you might say, how on earth could that actually be anything? Could that be anything reasonable? Could there be any structure to a thing where you're applying all possible rules? Well, it turns out there is. And actually well, so let me show you. Let's say we have a Turing machine. There's a little Turing machine. There are the rules of the Turing machine. There's the Turing machine doing its thing. This is a deterministic Turing machine, just does a definite thing. You can also make a non-deterministic, a multi-way Turing machine that has many possible paths of history. Its rules allow it to do more than one thing at each step. And this makes a multi-way graph from the Turing machine. You can also make a rulial Turing machine, rulial multi-way Turing machine, where at every step the Turing machine can do every possible thing a Turing machine of that type can do. And you can build up a multi-way graph here. There's an initial state. This has an edge for every possible thing the Turing machine can do. So from this, you end up building up this rulial multi-way graph of the behavior of all possible Turing machines. And there are many things you can conclude from this. I mean, one of the things that's interesting is to compare the deterministic Turing machines with the non-deterministic Turing machines. The P versus NP problem is basically the question of whether the red stuff here eventually extends as far as the gray stuff extends. But the main point is that this structure that you get, this Rullial multi-way graph structure, there's definite structure to it. Okay, so the ultimate limit is this thing we call the Rulliad. And the Rulliad is the limit, the entangled limit of all possible computations. So imagine all possible rules for doing the computation, all possible initial conditions for the computation, and you run it for infinite time. What do you get? Well, you get this thing that is this sort of necessary object. It has no parameters. It's just all possible computations, all possible initial conditions. There are different ways to coordinatize it. There are different ways to say, well, I'm going to parameterize it with Turing machines. I'm going to parameterize it with hypergraph rewrite systems and so on. But in the end, it's the same object. And what you realize is that we, embedded within that object, we are observers who are taking certain slices of that object. And that is how we perceive the physical universe to be. It's slices of this Rulliad object. And one of the things that's sort of a critical fact is that the reason that we perceive the universe to be the way we perceive it is because we are observers of the type that we are. So there are two conditions which are needed. One is that we are observers who are computationally bounded. The other is that we are observers who believe that we are persistent. That is, who believe that there's sort of a single thread of time that we exist through. Now, in this model, that we've got atoms of space that are continually being rewritten at 10 to the 100 times per second or something. So why do I think it's the same me now, a second later, as it was a second earlier? Because I'm made of completely different atoms of space. But it is nevertheless my view as an observer that I'm the same me. And similarly, when we move around, the possibility of pure motion, that you can take an object and just move it to a different place. It's made of different atoms of space. How come it's the same object? Well, it's a non-trivial fact about the model that motion is possible. It could be the case that when you try and move an object around, the object will get shredded immediately. And indeed, even in general relativity, if you're near a space-time singularity, any object will get shredded. The space-time structure is such that it no longer can be considered a sort of object that hangs together. So it's a non-trivial fact that in the end, that it is possible to be an observer who believes that they are persistent, who believes that there is pure motion, so to speak. Once you are such an observer, the very interesting fact is that from this underlying structure of the Rulliad, which is this necessary thing, it has no parameters, nothing. From that, once you have observers like us, you inevitably have general relativity and quantum mechanics. So I consider that to be a kind of a pretty interesting fact. So actually, you can go even further. This Rulliad object represents not only all possible physics, but also all possible mathematics. Because if you look at this structure that is you can think of this multi-way graph as being like a theorem-proving graph. So you can say, if we have, let's see if I can pull one up here. Let's see. No, I find one. I can generate one very quickly, but let's see if I can just find here. I'll pull one up from here. This book is nearly 20 years old now. Let's see, there's a good example. Okay, so this is a proof of a particular theorem in a version of Boolean algebra, where there are the axioms and you're saying, I can get from here to there by applying these axioms. But in general, I can make a multi-way graph that represents all possible ways to apply those axioms. And then a proof becomes a path in this multi-way graph. So mathematics, we can think of axiomatic mathematics as a story of setting up a particular multi-way rule, and then we say the proofs, the true theorems of mathematics are the paths in this multi-way graph. Actually, it's slightly more elaborate than that. The better way to set up mathematics is a little bit different from that, but that's a good first approximation. But the end result is that sort of the structure of mathematics then becomes a story again of it is another instance of the Roolead. And so basically what's happening is that what's happening is that there's a thing about the Roolead. There's a nice artist's impression of the Roolead. What's happening is that mathematics is coming from another sampling of the Roolead by essentially a mathematical observer. And so one feature of mathematics in the Roolead is that the mathematics could break down into all these different axioms and all these different sort of micro derivations of things. But it's an important observation about mathematics that you can do mathematics at a sort of a level of talking about mathematical objects and structures and so on. So, you know, you can talk about the Pythagorean theorem and you can talk about triangles and things like that, even though at the lowest level, when you represent that in terms of axioms, you're talking about how do you define a real number? There are all these different possible definitions you could use. There's a whole sort of cloud of axiomatic definitions that are all called by us the Pythagorean theorem. Now, just like I've talked about moving around objects in physical space, when you use the Pythagorean theorem and you go and you sort of transport it somewhere else mathematically, is it that whole cluster of points that sort of move together as this object that represents the Pythagorean theorem, or does the Pythagorean theorem get shredded because all those different axiomatic bases for the Pythagorean theorem all lead to different conclusions elsewhere in mathematics? The important point is that for the same reason that we perceive physical space and general relativity, we perceive that it to be possible to do sort of higher level mathematics, that we do not need to go down to the level of the axioms, or actually there's a level far below the axioms where we're building everything up from these essentially atoms of existence that are the same thing as the atoms of space in physics, but they're the things from which we will build things like the number one and so on. You can imagine building those. A good way to think about that is in terms of foundational ideas of computation theory, like combinators and so on. You can build those things up from these sort of computational foundations, and then you have this axiomatic layer. Then you get to the layer of sort of human-done higher mathematics, and the fact that it is that human level mathematics works, the fact that the Pythagorean theorem is not shredded, is the same reason that motion works in physical space. It's the same formal structure that leads those two things to happen. And they both happen because observers like us and physical observers like us, mathematical observers like us, also have many of the same attributes as physical observers. And that's why the same thing is observed of kind of this coherence of mathematical, sort of a coherent propagation of mathematical ideas. Well, I just mentioned, let's see if I can find this here. I just mentioned sort of a even bigger picture of this, perhaps. This has to do with kind of the paradigm, the computational paradigm that is defined by kind of these ideas about physics and so on. And I kind of think that sort of one can identify kind of four periods in sort of thinking about modeling of things. The first is kind of the one in antiquity where the basic question was, what's stuff made of? And that's the paradigm, the sort of structural paradigm for making models. It's the paradigm that many areas of science are still in. But it doesn't talk very much about time. It just says, what are things made of? It doesn't talk very much about the dynamics of how things change. Then we get to the 1600s and the kind of mathematical idea of, well, we'll just write down an equation to describe things. Time, in that case, enters, but it enters essentially as a parameter in the equations. You can just dial time to be whatever value you want. Then 1980s, my own efforts, is sort of this computational modeling idea, the idea that one should be able to use programs instead of equations to model the world. And that idea, despite people saying couldn't possibly work, it seems like in the last 20 or so years, pretty much every new model that's made of things nowadays is made with programs, not with equations. So I think after 300 years, it kind of rather silently, there was this transition from sort of equation-based modeling to program-based modeling. One feature of program-based modeling is that the notion of time is a bit different. You have a program, you run the program, there is this sort of irreducible computational process that takes place, and it isn't the case that you can just sort of dial time to be the value you want. Time is an inexorable process. Well, so the final story here is this multi-computation story. which is this idea that there are many threads of time, and to even tell what happened, you have to have an observer who is somehow knitting together these different threads of time. And that idea seems to have implications not only for physics, it's a foundational piece of our model for physics, also in mathematics, in the foundations of mathematics, but also a whole bunch of other fields. And this is not well worked out yet, but I'll mention some of the application areas. And it's really quite interesting that a lot of sort of the thing that's blocking a bunch of fields seems to be somewhat related and maybe related to this. So I'll mention one. Let's talk about chemistry. So in chemistry, we imagine a bunch of molecules bouncing around, they have reactions with each other. We actually make things like multi-way graphs in chemistry. Those are reaction networks in chemistry. And when you do chemical synthesis, you're asking, can I find a path through this reaction network that will get me to the chemical product that I want? But actually, we can go much lower level than that. We can think about each individual molecule and its interaction with every other molecule. And one feature of ordinary chemistry is we don't take account of every individual molecule. We just say, I just want to know the concentration of all these molecules. But in fact, there's tons more information in what's happening at the level of individual molecules. Molecule A collided with B, and then A collided with C and B, and so on. And there's a whole causal graph of interactions that happen at that kind of at the level of at this sort of individual level of molecules. And so the question then is, well, does that matter? Is it sufficient to just look at the overall chemical concentration, or does it matter what's happening in this kind of causal graph and so on? Well, molecular biology kind of has sort of an indication that there might be something else that one needs. I mean, if you go back, well, I don't know, 70 years or something before DNA was known about, people just say, well, there are a bunch of molecules that exist in biological material. And then it was discovered that one of those molecules can actually store digital information. There's more stuff going on in these molecules than one thought. Well, it seems very likely that the dynamics of these molecules at this microscopic level is also something that can be important. In a sense, it's going below thermodynamics. It is looking at the Maxwell's demons, so to speak, of individual molecules and asking what effect that has. And so, for example, when you look at biology, you can look at things like cell membranes and other kinds of things where actually things happen with individual molecules. And the question is, what is the kind of molecular biology observer? What is the thing that matters in molecular biology that comes from potentially this multi-way graph of possible interactions? And so one area that has sort of immediate potential application is in immunology, where one has this kind of shape space of possible antigens and antibodies. We've got 10 billion kinds of antibodies, and we have this whole set of pathways and things. And the question is, can one think about sort of the evolution of kind of in shape space in terms of these multi-way graphs and so on? And I think the answer is very likely to be yes. And it's kind of an interesting, leads one to a collection of interesting models of immunology, which we haven't worked out yet. But, and these things also relate to things like molecular scale computing and so on. But there are a whole bunch of other application areas where essentially this multi-computation idea is important. Or it looks like it'll be important. I mean, there's another one, which is to thinking about parallel computation. One of the things that, we usually, even, in Wolfram language, for example, we try to represent sort of everything in the world computationally. It's, we've been building this computational language, different thing from a programming language. Programming language is a lower level kind of idea of, you're just writing things that, deal with the hardware of the computer. Kind of the concept of our computational language is you're representing things in the world, whether they're cities or chemicals or graph structures or whatever else. And those are the things that you're operating on in the language. And those are the things that the language knows about. And but one of the issues is how do you represent processes in the language? And that's something that usually the role of the language is to kind of take the way that we think about things as humans and see how to use that to make use of computation to understand the world. But there's sort of one of the sort of frontier issues is how do you think about things that are happening in a distributed way? How do you kind of make a language around this kind of idea of multi-computation? It's something that, in a sense, is very incompatible with us humans, because, as I mentioned, the whole sort of thing of building a single thread of time, having kind of persistence, is a thing that seems to be critical to our way of constructing physics and so on. And so, in a sense, by asking how do you program going beyond that, you're asking to sort of go outside of what is normal for us humans to be trying to do. Now, I have no idea whether what I've talked about here is relevant to you guys. I was trying to give you a little bit of a summary of some of the things we've been up to. This is there's much depth of information on lots of these areas, and I'm happy to chat about whatever you'd like to chat about. But I think that's all I had to say here. So please, comments, questions, anything.
Yeah, that was brilliant. Thank you very much. It makes my mind spin in a way, but yeah, and thank you for your work and for pursuing this. You know, it's. I
wasn't planning to do this at this point in my life, I have to tell you. It's been interesting because I've done science, technology, every little bit less than 10 years. I've so far done 5 iterations of alternating between science and technology. And that's, you know, I started off working in physics, theoretical physics when I was a teenager in the 1970s. And that led me to want to make computational tools to be able to do physics better. That led me to build my first, essentially, symbolic language back in 1979, 1980. That got me to understand things about sort of computation and foundational ideas about computation. That got me, when I started thinking about sort of natural science again, got me to think about, well, what kinds of models could we actually use as the underpinnings for natural science? And that led to things like cellular automata and sort of thinking about things more computationally, which then in turn led to the creation of Mathematica, which then led to me to be able to do a bunch of the work that led to the big book, New Kind of Science, that came out in 2002. That was kind of made possible by the technology that we built in Mathematica. And then that book led to things like this principle of computational equivalence, which led me back to something I'd long thought about, which is, can we make sort of all the knowledge in the world computational? And I thought we'd have to build, you know, a whole AI to be able to do that, a whole kind of general brain-like AI to do that. But I realized if the principle of computational equivalence is true, that shouldn't be the case. So we should be able to do it with just computation. And that's what led me to start building Wolfram Alpha, which our computational knowledge engine, which then in turn led us to the whole modern Wolfram language, full-scale computational language idea of kind of having a representation of everything in the world computationally, and having a language which is sort of the bridge between us humans and kind of what's possible computationally. Then that in turn led to the fact that I had the technological tools to basically do the experiments that led to this current theory of physics. And together with, bizarrely, this whole question about, you know, these reference frames and causal graphs and updating orders and so on, that turns out to be a problem that I had thought about way back when I was working on my first symbolic language in 1979. I was really interested in what would the evaluation order be when you have something, you're doing a computation, what do you evaluate first? Turns out that problem is the exact same problem as the problem of local gauge invariance, the problem of general relativity, a bunch of these other problems. So in fact, what I realized many years after the fact was that back in 1979, I was thinking about 2 problems, which were actually the same problem, one from the particle physics side, one from the side of language design. And it took me 40 more years to realize that they're the same problem. And I think that's, please. Looks like Garrett had his hand up. So Garrett, please.
I've been fascinated by this stuff since you first came out with your book and have too many questions. So let me just ask one at least now. You had written that the same stuff that corresponds to virtual particles is actually making space. And so I have a question about zero-point energy. Mm-hmm. If we are tapping zero-point energy, if we figure out a way to tap zero-point energy locally, Are we taking that energy away, and can we continuously do it locally? Is it fed globally? What does your model say about
You know,
it?
back in 1981, I wrote this paper with a chap called Jan Ambjorn about zero-point energy. It was called Mechanical Properties of the Vacuum. And it was we were looking at the Casimir effect in boxes of different shapes. And I thought it was a little odd that we looked at these boxes and we changed the shape of the boxes and so on, and we could see these energy surfaces. And a number of years later, a chap called Robert Forward noticed that if you took those things from our paper, that you could do this closed loop and you could basically get energy out of the vacuum by just going around this closed loop and changing the sizes of boxes. And so there's a whole literature tree that seems to have developed about that. I mean, in the end, that isn't really a going concern, because the fact is, to make that work, you have to have a box that is opaque to all modes of the quantum field, including arbitrarily high frequency modes. And that's just not something you can make out of a material thing. So now the question is, in our current theory, first of all, virtual particles are kind of at the level of kind of the atoms of space, you're continually seeing sort of bubbling around of different structures being produced, other structures being produced, disappearing, etc. A virtual particle is something big enough that you can identify it as a definite particle-like thing. There are lots of these fluctuations happening right down to the smallest scales. There are fluctuations happening down to the level of individual atoms of space. An electron is probably a lot of atoms of space. An electron is maybe 10 to the 30th atoms of space. It's a pretty big object, probably. We don't know for sure these scales. But so that means that every so often there's going to be a fluctuation that's big enough that you can say, oh, it's like a virtual electron-positron pair. Most of the time, those fluctuations will be much smaller than that. So the question that you might ask, I suppose, is can you, if you put material into space, if you have parts of space that have a structure that is somehow persistent, like in the Casimir effect, you have the walls of the box or something, how do you think about that in terms of what effect that has on kind of the sort of the rest of the space? So actually, one thing I've been, when Jan Ambjorn and I wrote these papers back in 1981, we said it was going to be a series of 3 papers. We wrote 2 of them. The third one, Jan has been getting requests for versions of the third paper ever since then. And the third paper was going to be about the gravitational properties of the vacuum. And I think finally now I know how to write that paper. And the basic issue is, when you think about things purely gravitationally, so to speak, so you're imagining, for example, Casimir effects with black holes, things like this. Well, how does that work? When the boundary is not a metal box that you've just sort of imposed from the outside, but when the structure of space-time is what's producing, in the case of, in our models, the metal box is something which in our models is something about the structure of space-time, but we can get kind of a more a more uniform model of that by first thinking about what happens when we take, actual known configurations of space-time like black holes and look at Casimir effects and so on there. But so, I mean, in answer to your question about whether, I looked a little bit at the question of whether we can have, for example, can we have dark energy in our models? Dark energy has to correspond to a place where the amount of activity in the network is lower than it normally is. Mm-hmm. So in the network, probably 1 part in 10 to the 120 of all the activity in the network is stuff we care about, like electrons and so on. The rest of it is all just knitting together the structure of space. So we're a tiny blip on top of knitting together the structure of space. Now, if something will cause there to be less activity in knitting together the structure of space, then that will manifest as dark energy, basically. That will manifest as a cosmological constant. It'll manifest as a negative mass piece of the universe, so to speak. So but I don't know. I mean, it's an interesting thing. I mean, somebody at our summer school last year, I think, did some study of the Casimir effect in our models, but I think it's rather incomplete, and there's much to be done there. I mean, I think it's something where I feel like, okay, so the real question is, how much do you have to do what kind of analysis? So I had thought that analyzing things about energy, for example, would require that we know what particles are. Turns out it doesn't. There's a bulk notion of energy in our models. So the question is, what do you need to set up a kind of good Casimir type question? And I think probably it's quite possible we have what we need, in which case one could actually work out the gravitational Casimir effect and so on, and one could figure out, because there's going to be, but by the way, another prediction of our models is this black hole wind, which is a weird effect where basically there's momentum that is coming out of a black hole that is, let's see, I've talked about it in some piece that I wrote, but we have not worked it out in tremendous detail, but it is a quantum effect in our models, a quantum gravitational effect in our models associated with black holes. Probably too small to measure, but nevertheless a phenomenon. And I think there'll be a sort of a gravitational analog of the Casimir effect that will happen because of essentially the structure of space, having nothing, so, in our models, the structure of space and the fluctuations of quantum fields are ultimately the same thing. But to say we've got a fluctuation in a quantum field at the level of Feynman diagram that might be, a little bubble diagram or something that we might write for a Casimir effect, that's the very rare fluctuation that we can actually identify as being an electron-positron pair, as opposed to most of the fluctuations that are just knitting together the structure of space. So it's a very interesting question, and I don't have a good answer to it, but that's at least the beginning. And it is my guess that, around now we should be able to formulate enough to be able to actually address that within our models. And it's a good exercise, more than an exercise. It's a good research project. Thanks.
Yeah, I think George had a question. George, did you have a question?
Yes. Thanks very much, Stephen, for that very interesting talk. I have two questions that are related in sort of scale. One is in your your automata graphs. You talked about say arriving at Navier-Stokes, or some relation to Navier-Stokes. I take that as an example. At what point in your connection graph do you say, that represents Navier-Stokes? How do you relate the development of a graph to an actual physical theory? I didn't, unless I missed it, I didn't see. There's where Navier-Stokes comes in, or and I got a second question too.
Okay, so for example, this is, oops, let me move this here. This is a simple cellular automaton. This is really a different kind of thing. Navier-Stokes, that was an example. It's a kind of a motivating example, not the thing of what's going on in space-time. But in this case, this is a little cellular automaton, and you aggregate it up and you look at the average behavior, and you can find out that the average behavior of a velocity field corresponds to the velocity field for Navier-Stokes. And the more microscopic particles you include, the more accurate the approximation will be. And it's the same kind of thing in getting the Einstein equations. It's the same story of, I think I might have some other pictures here. This is from a long, long time ago. There we go. There are some pictures of if you look down underneath. Okay. This is, there's a bunch of very interesting science behind this, but this is, if you look down underneath here, eventually you just see a bunch of cellular automaton cells. But in the aggregate, just like we see in physical reality, we see a fluid flow, but there's actually molecular underneath. There's always the question of like in fluid dynamics, there's the question of, do you ultimately see through in turbulence down to the molecular scale, or are you only seeing fluid effects? But I'm not sure I understand. In the case of, for example, I could probably pull up Jonathan's paper about numerical relativity. Let's see if I can find that.
Well, you could leave it here. My question was, what we're looking at there was an actual diagram, let's say, of fluid particles flowing, which represents a solution to Navier-Stokes. Whereas the graphs that you've been showing are all graphs of interconnectedness of atoms of the universe, you might say. What's the relationship between the two? How did you get from atoms of the universe and these interconnected graphs to that that obviously physical representation of
All right, so let's say you want space-time, okay? The way you characterize space-time is with things like curvature. In this graph, the aggregate growth rate of those geodesic balls is what determines. I wonder whether Jonathan has a picture here. Let's see, those are just hypergraphs. Let me see what I can find. I'm sure he has a picture. Here we go. So this is somewhere down there is, okay, so that's showing, I think, one of these graphs, but the coloring is based on looking at certain average properties of the graph. Okay, so the graph is just the graph, but it's colored, the nodes of the graph are colored based on things about their connectivity, basically. So the color is just applied to the graph. The graph is the underlying thing. The coloring is just a way of kind of aggregating, a way of observing the graph in effect. And so then the point is here that I think these are, okay, so this is a black hole. So somewhere here is probably a black hole solution, and someplace here might be, if we're lucky, I don't know, might be, yeah, I mean, this is part of the evolution of two black holes. And again, I think the way it's drawn and the way it's colored is sort of based on certain intrinsic properties of the graph. All that really exists in the model is the graph, but it is the aggregate effect which we observe to be something like the curvature of space or whatever. That's how it works.
Okay, so we can go from the abstract of the interconnection graph to a less abstract, an actual physical representation, as you've just shown. My other question, I hope quickly, is that I was very surprised to find that your presentation arrives at or confirms virtually all of physics as we know it. Why does it not show us new things that aren't in our, or you haven't described it? It seems remarkable that, gosh, we've been able to show Navier-Stokes, for instance, and we got Cauchy, Riemann, and we've got Einstein, and we've got quantum mechanics. Isn't there anything new that
absolutely
that goes off in completely different directions that you didn't talk about, perhaps?
Well, right. So, I mean, several things to say. First of all, to know whether you're right, you have to know whether you fit into existing physics. Existing physics has gone a long way. It'd be crazy to say, I'm going to make a theory of physics and I'm going to compare it only with 19th century electromagnetism or something. You want to be able to compare it with the best that physics has been able to produce, which is general relativity, quantum field theory, things like that. So that's an important piece, is can you make connections with existing physics? The second thing is, what things can we imagine? There are things which the model inevitably implies, like, for example, dimension fluctuations in space-time. That's an inevitable consequence of the model. How big they are, whether they're observable, we don't know. But that's an inevitable consequence of the model. There are a whole bunch of consequences about things about black hole horizons and so on that are sort of inevitable features of the model that are indeed, some of them are things people have suspected and conjectured from quantum field theory, but they're things which are sort of inevitable in this model. I think that one of the questions is, what is it that, there are no doubt experiments which are wonderful, magnificent, unexpected experiments. I'm sure, when people first started looking at Brownian motion, for example, it wasn't an obvious experiment to do. And so, there are no doubt obvious experiments which will show us, oh, why didn't we think of that? I mean, like, for example, we have a suspicion that photons orbiting spinning black holes will have different properties in our models than they do in traditional general relativity plus quantum mechanics. It's a fairly subtle effect. It happens to be bizarrely similar to the effect that sort of confirmed general relativity from the bending of light around the sun being a factor of 2 larger than you would otherwise have expected. We expect that certain correlations for photons in orbit around black holes will be a constant factor different from what you would otherwise have expected, rather than a factor that depends on unknown parameters. So those are a few things, but the thing that I think is the big thing to say is, it's it's kind of hard. It's like asking to invent technology where you've said, just invent a piece of technology. It's like invent an experiment that you could do that would, that will have a dramatic effect. We can see certain things like dimension fluctuations where it's sort of inevitable that something like that will be there, but other things require creativity that we, that's another creative act beyond coming up with the original model. Now, another thing to say is that the way we parse the universe, the way we take all those atoms of space and we do the thing that you were asking about, of how do we figure out, it's a very fundamental thing. How do we go from the atoms of space to something that we can perceive, like curvature, like fluid flow, or whatever else? How do we do that? Well, we do that by being observers of a certain kind. If we were different kinds of observers, we would conclude completely different things about the way the universe works. And so one of the consequences of this thinking is that the reason we have the laws of physics we have is because of the kinds of ways that we perceive them. And not to some, let me give you an example. The fact that we view the universe as progressing through time where all of space is known at a particular time. So for example, we imagine that there's space and it progresses through time, okay? That's a consequence of the way that we perceive of a very specific thing. We look around, we might see a few tens of meters away, hundreds of meters away, maybe. But the time that it takes light to come from 100 meters away to us is very short compared to the time it takes our brain to process the state of the world. So that fact is why we typically think of things, all of space progressing through time. If it wasn't like that, if we were much bigger and the speed of light really mattered more to us, we wouldn't have that view of space, that it's sort of things happen simultaneously all across space. If our primary sensory system was olfaction, we'd be waiting for the diffusion of molecules and we'd have a different view of how space works. So, part of our conclusions about the universe have to do with the way in which we perceive the universe and even the particular sensory systems we have. And one of the things we're doing right now is looking at metamathematics and looking at the correspondence of this with mathematics. And it's really, in fact, it's my project for the remainder of the day, is trying to do an experiment in metamathematics. So basically, we know there are 4 million theorems that have been written down in the history of human mathematics. Those are like, if we think about metamathematical space, like physical space, those are like the places we visited in physical space, the places we built cities on the Earth, for example. But if we observe the 3D coordinates of all the cities on the Earth, and all we know is where people built cities, we could conclude a much bigger fact, which is they're all on the surface of a sphere. And so the question is, from metamathematics, can we actually conclude things from empirical metamathematics, can we conclude things about what's underneath? But so there are very bizarrely different kinds of experiments that you can imagine doing that tell you things about the structure. And I think from the point of view of physics, yes, it's a big, somebody is going to figure out a really cool quantum experiment, quantum many-body experiment, which is going to show the maximum entanglement speed, and that will be fantastic. But I haven't figured that out yet. That's still for the future to figure out. And again, we don't know the scale of the maximum entanglement speed, so it might be really hard to measure. It might be comparatively easy to measure. Just don't know yet.
Thank you.
So to just sort of follow up to George's question, you haven't seen any hints yet of a new way of generating forces or energy, something different than what our standard physics predicts. And I understand and I agree completely. You have to match everything that we've already done before you move on to something new. So has there been any hint?
That's a good prompt. So it's a good prompt. Can I imagine? I mean, I did the exercise. I had agreed to give a talk at some NASA workshop, when was it? In 2020, actually, about where I had rashly said, I'll talk about faster than light travel. And so I did think about, I mentioned some of the conclusions from that.
Right.
And that this question of, sources of energy. Okay, interesting prompt. So let me think for a second. I mean, in, what you've basically got to do, okay, so obviously, in our model, energy is associated with this activity in the network. It produces curvature in space-time. Energy always produces curvature in space-time. That's not surprising. The question is, can you, I guess the issue is there something you can do to, increase, for example, the energy density? Let me think about this for a second. I mean, clearly there are effects that have to do with dimension fluctuations that will be totally bizarre, and which will be where, and it's a good question whether you can make, for example, can you make a closed cycle that uses space tunnels to, and for example, energy conservation is not a trivial thing in our models. Energy conservation isn't trivial in general relativity either. Energy conservation is a complicated story in general relativity. What it means to have. So, for example, here's an example of an issue. So, here's a way to make huge amounts of energy. Okay, take two galaxies that are far away in the universe and attach a string between them. Okay, there will be that spring or whatever will be put under more and more tension as the universe expands. Okay. Well, unfortunately, it's really difficult to put a spring between two galaxies out of the local cluster and so on that are subject to the overall expansion of the universe. But that's an example of a place where energy conservation, traditional simple-minded energy conservation, simply doesn't work in general relativity. There is the Hubble flow violates what you would normally think of as energy conservation. So similarly, in our models, one of the more bizarre things is that there's also presumably expansion in branchial space. And it is quite possibly the case that if quantum computers are going to work, they have to work through essentially expansion in branchial space. That without that, you end up spending as much effort measuring the results of your quantum process as you do having parallelism in the making of the quantum result. So the question would be, can you hitch a ride? We don't know how fast branchial space expands, no idea. That's related to this maximum entanglement speed and so on. Could you hitch a ride in branchial space and use the expansion of branchial space to more, with less effort than it takes to string something between two galaxies? Right? And we don't know the answer, but that's an example of a type of thing you might imagine. That is, you're using you want energy here. Well, the universe is providing lots of energy by virtue of its overall expansion. And in our models, that overall expansion is associated with, well, the overall activity of the network, because it's the thing, it's making more atoms of space, for example. And so, I could imagine, so I think, a reasonable thing to do is to imagine, can you hitch a ride on the expansion of branchial space? So what would that actually look like? That will be something like, how would that work? You would have to, let's see, within different quantum degrees of freedom, you would have to somehow figure out how, okay, so one of the things we don't know the answer to yet is the layout of quantum degrees of freedom in branchial space. And for example, when you try and do the double slit experiment, what seems to be happening there, this is kind of interesting and very bizarre, is that that's a case where branchial space is mapped, that there is a map between branchial space and physical space. And what's essentially happening, so how does, for example, destructive interference happen? You've got two photons, they're going through the two slits, and it turns out what seems to happen is those two photons, they end up in the same place in physical space, but they end up in opposite ends of branchial space. So what? Well, the point is, as an observer, you are of bounded size in branchial space. So as an observer, you're saying, what happened? I want to know what happened. I'm looking at this little region of branchial space. Well, the problem is, if the photons, if those two photons wound up at opposite ends of branchial space, you'll not see either of them in this little region of branchial space that you're looking at. So the sort of cause of destructive interference is that you wind up with sort of taking these degrees of freedom and throwing them to different ends of branchial space. So the question is, if you ask the question, could you do the opposite of that somehow? And well, okay, that's an interesting idea. So, I mean, the kind of thing you would imagine is some kind of concentrator in branchial space, concentrator of quantum degrees of freedom in branchial space. So I think, you know, I could imagine there's some effect there. I could even imagine that there's some Casimir-like effect there. I don't know. But so that's my off-the-cuff effort at inventing a way to generate infinite energy. I mean, I think the thing to realize is, you know, why is it impossible to, you know, make a perpetual motion machine in thermodynamics? The answer, in the kind of whole stack of ideas that our models are based on, the answer is purely computational. That is, to extract mechanical work from a gas, all you have to do is be able to predict where all the molecules are going to be. Then you make that little thing with all these tentacles that's just knowing, oh, this molecule is going to be here, this one's going to be here, I'll make all these tentacles. And by the way, I think we can fully expect that there will be, you know, that there will be sort of violations of thermodynamics that will be the result of essentially building devices that are computationally more capable than we expected, and that make use of the fact that you can make predictions down at the level of sort of individual molecules, that isn't just heat that we don't understand. An exercise for
yeah, this concentrator of the degrees of freedom just really rings a bell with me. You know,
figure out how to do it. It's I can tell you one thing, that in branch Hill space, it looks like, one question is, can you make crystals in branch Hill space? That is, can you make things where they're quantum systems that have their degrees of freedom laid out in some organized way? And I think this is related to these things called tensor networks that are being used in for various kinds of quantum information discussions. But I think that there's that's sort of a question of what would it be like? What kind of a thing is a crystal in branch Hill space? Don't know the answer to that, but that would be a place to start, because yeah, I mean, it's the thing that's interesting about, okay, one thing that's great about this model of physics is that it's is that there are you know, you can do computer experiments, you can actually, you know, do experiments, you can see things, you can get intuition from those experiments, but the distance between those experiments and things that you can physically deal with, you know, if the elementary length is 10 to the minus 90 meters, there's a lot of elementary lengths that fit in, you know, that's a lot bigger than you can compute on a computer, but it's still, you know, the way this project is really working is it's going at things from three different directions. One is computer experiments where you can find out what actually happens, and they often surprise me. Another is kind of the sort of almost the philosophy of what's going on. It is not philosophically straightforward. I mean, all these things about, you know, the observer and how the observer relates to this or that, that's essentially a story of philosophy. And it's this kind of interesting effect that you're seeing the experiments, computer experiments, one end, you're seeing philosophy on another end, and then you're seeing mathematical physics somewhere in the middle. Those three things are the three sort of methodologies that seem to be important for this. And it's interesting to see them all come together. But the fourth piece is actually being able to do physical experiments, and that, you know,
on the scale that we can do here.
yeah, right. Well, I mean, you know,
or we can observe something somewhere, but, you know, much better if we could do it here.
Absolutely. And I mean, the question, the exercise, so I'll tell you a couple of stories. So when I invented computational irreducibility back in the 1980s, if you said, what's it good for? I would have said, well, you know, it tells one some limitations on what you can, you know, what you can sort of compute in physics, et cetera, et cetera, et cetera. What I would never have imagined is that a few decades go by, and I have reason to believe that there was a causal connection between the computational irreducibility idea and the idea of proof of work for blockchains, and the fact that you can sort of, that something irreducible happened when you go and, you know, try and find those hashes and so on. And I had no idea that computational irreducibility as an idea a few years later would lead to, you know, the burning of the electrical output of Italy or something in proof of work for blockchains. But it's the same idea. So it's very hard to, you know, that was a comparatively short period of time. It's always interesting to see, you know, these things which start as sort of basic science ideas, how they turn into sort of reality that ends up being relevant. And I've seen this, I mean, in this model of physics, my guess is that the first real applications of the model of physics will be to distributed computing, molecular biology, possibly economics, and areas where you'd say that why is that relevant? Well, the reason it's relevant is because by showing that there's a common formalism below all of these things, one gets to import the last 100 years of success in physics into an area like economics. In other words, if you can show that the underlying formalism is the same, then you can say, well, what's a black hole in economics? What's an event horizon? What's what is a Lorentz transformation, et cetera, et cetera, et cetera. And I think that's the, but I don't know. I mean, in terms of physics and technology, it's, I would love to know. It's a fascinating thing to speculate on. What, given this model of physics, what will be the first big technological application of this? I mean, we're still, for example, if you look at particle physics does not yet have, for example, let's say strange particles. So far as I know, there is zero technological application of strange particles. Even cancer therapy, maybe people use kaons a little bit, but not a lot. And that it's like when do these things, eventually probably, what is technology? Technology is taking things that we are thrown by the universe, so to speak, and finding ways to apply them for human purposes.
Exactly.
And so it's a question of what, where is that? So two things have to happen. One is you have to figure out, how do you take our existing human purposes and manage to fish out of what the universe provides the thing that we can apply. That's possibility number one. Possibility number two is human purposes evolve and we realize, oh gosh, we can make use of this thing that like people talk about using, gravitational lensing around the sun or something as a way to make a giant telescope, that kind of thing.
Right. Yeah, so I know Eric had a couple of burning questions that he's really anxious to ask you.
Please go ahead. I do have to go fairly soon, but I'm happy to.
Okay, thank you.
Yeah.
Hi, Stephen. I just want to make one comment.
Are you going to be on video? That will be. It's always lovely to see.
Well, I've lost one eye, and I'm not. I would like not to do that.
Okay, don't do that. It's all right. No problem. I'm just. Please go ahead.
I'm not looking very good at the moment with my removed eye. You can't cool a room by illuminating it with photons, and so the interference of photons is called into question. And one more thing I wanted to say is if you can drop the hydrogen atom to a stable state below the ground state, you'd increase the energy density of the hydrogen atom, and that might lead to an energy source. But the thing that I wanted to ask you about the Reuliad was with the Reuliad, can a node of the Reuliad have its nodal rule change to become different than the root rule of the Reuliad? And if yes, does that not invalidate the principle of computational equivalence? So
the Reuliad contains all possible rules. So its nodes include, each node, each event happening in the Reuliad happens, there is an event for every possible rule. It's a very big object. Interestingly, it's also an object that is very similar to one that's been considered in sort of the upper reaches of pure mathematics, a thing called the infinity groupoid, which is a thing that you get from the limit of higher category theory. And it's a thing where you're basically asking, you're asking for proofs of mathematical theorems, which are transformations from one expression to another. And then you're asking for proofs between proofs, transformations between proofs. And you keep doing that up to infinity, and you get an object which is essentially the same as the Reuliad. And that's something which has arisen in sort of the upper reaches of pure mathematics. But the Reuliad is a thing where every event is happening according to a particular rule, but all possible rules, there are events for all possible rules. Now, I have to say, coming back to what you were saying before about cooling a room with photons, I'm now curious what that even means. I mean, so
if photons interfere with each other, then the room would cool, right? They would cancel each other out.
Well, only if the only thing in heat is most of heat is sort of the motion of molecules, material particles, not photons. I mean, if you have a a room where the only thing in it is where it's, you know, it's a vacuum other than photons, then the question of what, I mean, that's you know, you have a room, imagine a room which has perfect mirror walls and it's full of photons and it's just a pure photon gas. And then I don't think, I mean, so you're asking the question, a pure photon gas I mean, in order to have interference in a photon gas, you have to have coherence. In order to have coherence, you have to define the thing to be in a certain quantum state. And so that means that, I mean, your average photon gas is not, you know, it's an incoherent collection of quantum states that correspond to photons being at some, effectively at some, I mean, let's see, the photons have an energy which defines, let's think about this for a second. I don't think, I mean, so an interesting question is, okay, I'll give you a more extreme version. So if you have a room and you're expanding the room and you're asking the question, you know, does the photon gas will obey the ideal gas law because photons don't interact with each other. The interference between photons is a consequence. Well, that's tricky. That's tricky. Yeah, because that's tricky because that involves a single quantum state, which is a different thing from, well, okay, I was going to comment that there is a tiny interaction between photons, the photon light by light scattering effect, which I don't actually know what sign it has, and I probably could figure that out some way. Comes from the Feynman diagram where you have two photons come in, they make an electron-positron pair, that electron-positron pair then annihilates into two more photons. That leads to light by light scattering. It's a very small effect, but it is an effect. And so that means that photons are not completely an ideal gas. And you would expect that. So it's a good question whether a photon gas, if you expand the walls of the photon gas and you account for light by light scattering, does that lead to cooling or heating? What does that lead to? That leads to, oh yeah, right. So light by light scattering will any scattering effect like that it will retard the phase of the photons. So the photons come in and they're messing around doing their light by light scattering, and then they'll come out with a phase that is behind the phase that they would come in at. So that means that means it's like I think it's like, well, that's a good question. It's I would guess that it's like an attractive interaction, which means that the gas would cool. But I don't know how to think about it in terms of interference between photons, because as I say, interference is not something you get with photons randomly bouncing around a room. You need coherence in order to get that. But I mean, another effect, you can have a much bigger effect if you were to have not photons, but gluons. I mean, most of that wouldn't be, you know, the gluons don't get to fill the room because they are confined and they get to make little glue balls and things. But that would be an effect where you would have, you know, dramatic cooling in a sense. Anyway, sorry, that was just excuse me for that physics riff. An interesting.
Well, also when the photons hit the wall of the room, they don't bounce off. They interact with the electrons and cause electronic transitions. The other question I wanted to ask you was really quickly about time dilation, gravitational time dilation. And maybe this is not a good question because time is different in your model, but if you have a computer on top of Mount Everest, it's going to be able to make more computations per unit second than the computer at the surface of the Earth, because the time's running slower at the surface.
Absolutely.
Is that accounted for in your model, and is that really relevant?
Yeah, absolutely. I mean, you know, the center of the Earth is, I don't know how much it is. The center of the Earth is a few seconds younger than the surface of the Earth, if I remember correctly, as a result of the gravitational redshift. And that effect is actually very intuitive in our models, because what happens is, in the presence of a gravitational field, let's see, I have to get the sign of this right. Let's see. Yes, I mean, there's an intuitive argument for why time runs more slowly in the presence of I have to get this the right way around. Let's see. Time runs more slowly in
gravity. The stronger the gravity, the slower the time.
Right. Okay. So that, I think, is the way you understand that in our models is because essentially some of the computational effort that is, let's see, this is a very simple argument, and it's written down in a bunch of things I've written, and I should be able to reproduce it. But basically you're spending effort as a result of, you essentially have a higher density of events associated with the gravitational field. And that means that there is, if you compare, I think that means that time is running faster. I'm sorry, I'm not getting this the right way around, but there's a very simple intuitive argument in our models based on the interpretation of energy and the interpretation of curvature for why gravitational redshift works the way it does. And you can nail that down.
Does that break
More
computational equivalence?
That's why.
Say it again, sorry.
Does that break computational equivalence when you can have one computer running more computations per unit second than another?
No, because that's I mean, the principle of computational equivalence is a floppy thing, in the same way that the question of whether, what it says is if you go for a sufficiently long time, for example, then, I mean, again, it's like P versus NP problem and things like this. It isn't the case that you can, any particular computation you may be able to do quickly, but the issue is, if you look at the overall collection of computations, do they, for example, take polynomial time or more than polynomial time, those kinds of questions. It's something which on a sort of single case basis is not such an easy thing to answer. And people have been, I mean, this whole question about how to nail down exactly how principle of computational equivalence works in different kinds of systems, people have been writing papers about that for the last, I don't know, 30 years or so since I introduced this idea. There are lots of them and lots of different particular ways to pin it down, most of which have one problem or another, one sort of slight pathology or another. But so it's not something where you can start saying, where you can start tracing things at that sort of microscopic level. It just like if you talk about the law of entropy increase, you say, well, let's try and nail that down. Let's exactly how coarse-grained does the system have to be to get that? Well, it depends. It's complicated. It's not such a straightforward thing. It's I mean, there's vastly more to say about this, but that's the bigger picture. Okay, let's
All right, thank you, Stephen. It was quite an honor. Thank you.
Let's see, Thorsten, I think.
Say a few things shortly. Thank you very much. It's very interesting work. I see very interesting similarities to what Nikolai Kozyrev came up 70 years ago. I don't know if you know about this Russian professor. Yes, he made in the 50s a new physics out of thinking, which he called causal mechanics. And his basis was the properties or the propagation of cause and effect. And he came up with three different light speeds, so to speak, one light speed, then one speed of cause and effect that he measured. And from those experiments, he came up with predictions. And he actually found, for example, lunar volcanism that was not found before. And he found some other very interesting things. So you can look it up if you're interested. The main thing that I think is very interesting here is that Kozyrev, in his essence, came to the point that time is much more than just a mechanical clock. It has a lot of similarities with what it's like an energy, or it can cause effects, so to speak. But I see more similarities, and I think if he didn't have any computers, but I'm sure if he could have joined with all your findings, that would be super fascinating. So Nikolai Kozyrev is that Russian professor.
How do you spell his last name?
Kozyrev, it looks like.
Yeah, and I wrote a paper about it. You can look it up on my ResearchGate.
Yeah.
Here's the person, I know this story. He's the person who didn't know about the discovery of nuclear energy. And okay. Right. Yes, I know this sad story. Yes.
Oh yeah, well, it's a sad story, but he also made some very interesting findings, which kind of correlate with what you're finding. You're finding much more, but I think, for example, his 3 different speeds and his measured speed of cause and effect might be of some use for you.
How did he measure it? What did he measure?
I measure dissipative processes and, for example, evaporation, dissolving salt, evaporation of acetone, and a bunch of other things.
Okay. I mean, those are, the challenge with these things.
The most fascinating thing for me, which caught me on that work, was that he found the true position of stars, because the 3rd speed is kind of nearly instant. So he could measure with his instruments, he could measure the exact position of the sun now, the position of the sun where we see it, and the position mirrored from that.
The problem with that is that the concept of now is a slippery one.
Yeah.
That's kind of what, that was kind of Einstein's point, that what is now? And that shows up in our models in terms of this arbitrary observer-dependent notion of, what counts as simultaneity in the causal graph and so on. But
he didn't say instant, it's like very fast, so.
Right. Well, I mean, the thing that is an interesting question for us is there are quantum experiments where, there aren't quantum experiments where you can have instantaneous propagation of information, but there are quantum experiments where you effectively have instantaneous sort of correlation of quantum phase. And actually in our models, that will not be instantaneous. It will be determined by something to do with the maximum entanglement speed. And that's another potentially measurable feature of what's going on. But, one of the challenges in this whole business of, sort of fundamental models of physics and so on it is a terrible thing that I do not understand very well. I get, at the rate of probably on average 1 per day, things from people saying, I have a fundamental theory of physics. And it's just a very frustrating thing, because I'm like, lots of effort has been put in. Most of those things that I get link only to high school level physics, which makes it sort of hopeless, because by the time you ignored the last 150 years of physics, it's very hard to tell whether you're talking about anything that makes any sense, because you've kind of given yourself a huge handicap. And I would say the minority have actual computations of any kind, but it's a thing where I have to say I've found it I really wonder, it's like there may be good ideas there. I have no idea. And it's, we have a polite form letter that we send back, and which basically says, look, you can find everything we've done, point us to particular places where what you've done might have some relevance to what we've done, and then we can understand that. And, write a piece of Wolfram language code that demonstrates this, then we can actually understand it. And I would say in a small minority of cases, including some very interesting people who have gotten involved with our project, actually, some people come back and say, yeah, I've got some code, I've got this, I've got that. And it's very interesting. But the vast majority, it's like, I would love to have a theory for what to do, because I just discovered actually that somebody has cataloged such, theories of physics. I think they have like 20,000 of them that they've cataloged. And it's from a human point of view, it's like clearly a lot of effort is being spent. And, I'd like to figure out, it's one of these places where it's like, how do you correlate that effort into something that, has longer term value? And I haven't figured it out. So if anybody has any great idea, I'd be, it's the thing that I find, is frustrating is the extent to which these things are based on really sort of, I would say, the ideas about physics that are pretty much high school level physics. And, the fact that, for example, in our project, the fact that our project has been doable is a direct consequence of the fact that, I used to be a a sort of a standard issue theoretical physicist, so to speak. So I know all this stuff about quantum field theory and general relativity and all that kind of thing, and I've known it since I was a kid. And it was kind of, that if you factor that out of what we're doing, it would not stand a chance, because it would be like, well, we can do these computations, but I have no idea whether this relates to, things in, is this something like a virtual particle? I don't really know what a virtual particle is, but I do know what it is because I, used to compute lots of things in quantum field theory and so on. So it's really it's an interesting challenge. Actually, one thing that I will say that one of the areas where I know there can be great contributions is in this field that I just given a name to, which is ruleology, the study of simple rules and what they do. And that's something that I kind of initiated in the 1980s, in the early 1980s, and that kind of broke off. A piece of it broke off into sort of complexity theory and kind of came upon somewhat crazy times, I think. But the idea of you've got a simple rule, you want to find out what it does, that's a thing which you can explore experimentally, you can explore it in a bunch of theoretical ways and so on. It's a very interesting field that is kind of a little bit like chemistry was at one time, where it's like, we've got a molecule, what does it do? Well, eventually it turns out people really care about that kind of molecule, but if you are dealing with fundamental enough things, it's sort of inevitable that they'll eventually have applications. And that's the way I feel about ruleology. And we just did a big study of, because I sort of initiated this in the 1980s, a bunch of people started working on it. We're now, 40 years later or whatever, and it's a lot of those people have done a lot of interesting work, but they are embedded in all kinds of random places in the world. There are no departments of ruleology, so to speak, yet at universities. So they're embedded in all sorts of different places. And we are about to initiate this thing we're calling the Ruleological Society, where we're just trying to collect people who have basically done this, very interesting area of science that I think is ultimately going to turn out to be sort of one of the most fundamental areas of science, but they've all been scattered around in all these different places. So it took me a few decades to figure out what to do with this, but I think we're going to have a good ending there. And I'd love to find the same kind of thing for theories of physics, but I haven't. Anyway, maybe one last thing, and then I should run off here. I think I'm getting reminded that I'm.
I think Jake has a question.
Yes, my question is, when we consider all the themes we are talking about now, we speak about the observer who perceives the time. What would physics would be, or mathematics, if we say there is no time? When would we take the perspective of no time?
Well, I mean, the way that humans perceive the universe is with the idea that we have an experience through time. In other areas, for example, in mathematics, time works a bit differently. There is a notion of time in mathematics. It has to do with successive steps in proofs and deriving one theorem from another by proofs. But a lot of the way that mathematics is done is more like extension in space than it is like progression in time. Mm-hmm. In the end, in this Rulead structure, everything is there. The question is, how are you perceiving it? How are you moving through it? And that's the thing that, and I think, in mathematics, I've just been writing about this actually. There's this. Okay, so there is a notion of entailment in mathematics. One theorem entails another theorem, and that's a kind of progression through time. And we have this notion of an entailment cone that is analogous to a light cone, where one theorem entails other theorems. There's also a notion of what we call an entailment fabric, where you have basically a simultaneity surface where you've got sort of theorems that you can simultaneously think are true, so to speak. And in a sense, quite a lot of the way mathematics is done has to do with knitting together pieces of entailment fabric rather than doing this sort of forward evolution of deriving things from other things. So I think that to the mathematical observer, there is a slightly different view of time. Just like, but I think in our experience, it's a key aspect of our way of experiencing the world, that it is through time, and that we remember the past, and we can predict the future to some extent, and but time is a key aspect of that. And I think it's hard to that's just a feature of the way that we parse the universe. We might do it differently, but our idea of time gives us the idea of motion, and it gives us all kinds of other features of the way that we understand the universe. To understand it, I unfortunately really need to go. Sorry.
Right.
It's
yeah.
All right.
It's been such a pleasure, Stephen. Thank you for a wonderful talk and taking the time to answer all our questions. And maybe we'll see you next time we're in Boston.
That's delightful.
Sounds good. Yes. Well,
Yeah.
it's you asked some interesting questions. You got me thinking about energy in our. So
Yeah, right.
invent the branch shield concentrator. That's
yes. Degrees of freedom concentrator. Yes, sir.
Yeah. Okay.
All right. Take
Bye-bye.
care. Thank you. Bye.
Is Jim walking?
I think Jim must be walking, but okay. Well, that was very exciting, and thank you everyone who stuck around for that. We start again tomorrow at 10 o'clock. The Zoom opens at 9:30. We're going to be talking about fluctuations, in particular vacuum fluctuations, so-called vacuum fluctuations, and I think some interesting other theories associated with pilot wave, et cetera, ways of thinking about things. So hope you can join us tomorrow. Thank you.
I wanted to say, just while some of you are still here, those of you who saw Marcus Buehler's talk yesterday with the 3D webs, I just kept thinking about moving through Stephen's hyperstructures, like Marcus was moving through those webs.
I wrote that down, right? Because Marcus is assigning something to
so
each,
much overlap.
Right. And it's just like what Stephen is doing.
I
actually.
know. Yeah. I just thought it was a really beautiful overlap.
Right,
what a treat, right? What a
Yes.
treat to have a chance to put our heads together with Stephen.
Yes.